Finished the first part of the course. Today I'm going to show you formulas for the prices of European put and call options, which is what I promised you at the beginning of this course. Now, to do that, we're going to roll up our sleeves and we're going to use all the tools and the techniques and the notions that I've been teaching you during the last few lectures. And let me take you to what happened last week. So we ended more or less here. We said, let's take a underlying asset price S, which behaves according to our model. This is our model of the evolution of prices. And let's have a look at the price of a derivative whose underlying asset is price S. And then we said, the price of this derivative is going to be a function of the underlying asset price and time. So that's that function we're calling little f there. And then if f is not going to be too bad, if you can differentiate it enough, then you're going to ask yourself, what is f itself? If you look at, instead of the price of the underlying asset of, say, a call option, if you look at the price of the call option itself, what is that going to be? So when we're looking at times t in the future, we don't know what the price is going to be. So what we're getting is a family of random variables indexed by time, which is what we're calling a stochastic process. And then we can use Ito's lemma to find what stochastic process that is. So if we take this function, which is going to be the function of some derivative, and we ask ourselves, how is f changing? Then the way f is changing is given by this. We just use Ito's lemma to say f itself, which is a function of an Ito process in time, is an Ito process, and df as this component proportional to dt, and this other component proportional to d Brownian motion. Okay, so now that's the proof of that, an application of Ito's lemma. So now instead of looking at an infinitesimal period of time, let's have a look at a very short period of time. Say a period of time which starts at t and ends at t plus delta t. And we can observe the change in the position of a particle following Brownian motion during that period of time. So we start at position bt, and then we're going to find ourselves in position b t plus delta t. Then we can talk about delta Brownian motion, which is going to be the difference of the two. And then if instead of talking about the infinitesimal period of time, we talk about a very short period of time, we can get a discrete version of the infinitesimal behavior by saying, okay, so over a very short period of time, the change in f is going to be that expression times delta t now, plus this other expression times delta b. And now, let's go back. Let's remember what happened when we were living in a very simple world. We had a world in which we were at time 0 here, and then one of two underlying assets were going to be observed. We didn't know which one. And then we were trying to find out the price of some derivative. We said, let's construct a clever portfolio which had delta units of the underlying assets, say delta shares, and -1 derivatives. And then let's choose delta very carefully so that no matter where you find yourself after one step in time, the value of the portfolio is the same. And if we managed to do that, and we managed to do that, that allowed us to find a formula for the price of this derivative. We're going to do exactly the same thing here. I'm going to show you a clever choice of portfolio. We're going to check what happens to this portfolio after a very short period of time, and it's going to have the same property as what we had when we solved this problem. If we choose the portfolio carefully enough, and we are going to do that, then the value of the portfolio after a short period of time delta t is going to be the same no matter which state of the world you find yourself. And that is going to allow us to come up with something which then will allow us to find the prices of these derivatives. So what is this clever portfolio I'm talking about? We're going to have some number of shares. So when we did the binomial trees, we had this unknown number of shares, which we call delta, and then we found the condition for delta. But now I'm telling you what the delta is. It's going to be dfds. So I'm going to do this at every point in time. I have this unknown function, which is going to be the price of the derivative, this f at the underlying asset price at time t and time. That's going to be the price of the derivative at time t. And then I say, well, look at some time t in the future and take df, the first variable, evaluated at s and t, st and t, at the price you observe at time t of the underlying asset and time t. So take this number of shares. Now this is a number. This is a function, and the derivative is a function. And once you observe the price at time t and time t, this is a number. So when you stand at time t, take this number of shares and put that in your portfolio and take minus one of your derivatives. Okay. So now we constructed this portfolio, and let's give a name to the value of this portfolio. Let's call it pi. So what is the value of this portfolio? Well, it's the number of shares, the number of units of the underlying asset, which is this, times the price per unit of underlying asset, which is what we're calling S. And then we have minus one derivatives. So the contribution of the derivatives to the price of this portfolio is minus F. Okay? Is this making sense? Does this look similar to what we've done in the case of binomial trees? Can you hear me? Okay, so now let's ask ourselves, what happens to this portfolio we just constructed if we wait for a very short period of time, for delta t years? So the value of the portfolio is going to change. Why is it going to change? Because it has two components in it. It has shares and it has a derivative in it, minus one derivatives in it. So the prices of these things is going to change, which is then going to change the value of the portfolio. So by how much does the value of the portfolio pi change over this period of time of delta t? Well, if the change in the underlying asset price is delta s, then we have dfds shares, and each one is changing its price by this much. We have minus one derivative, so if the derivative changes its price by this much, then that's going to give a contribution of minus delta f to the value, the change in value of our portfolio. And now let's write down what these things are. So we look at delta s. What is delta s? Well, ds, over the infinitesimal period of time, we said our underlying asset price satisfies mu s dt plus sigma s d Brownian motion. Over a short period of time, the change in the underlying asset price is going to be, well, mu s times delta t plus sigma s times delta Brownian motion. That delta Brownian motion from here. Okay, so we know what to write instead of delta s. It's this. And delta f, we've just computed using Ito's lemma. We know exactly what delta f is. It was in the previous slide. So we write down everything we know. So we have the change in pi, and the change in the value of the portfolio is dfds, this number dfds times the change in s, which we estimate by doing this, minus whatever expression we had before for delta f. Now, this looks a bit hopeless. This is a very complicated expression, except that you notice that lots of things are going to cancel. And that's where I chose my portfolio cleverly, so that these cancellations will occur. So let's see, what is getting cancelled here? So let's see, we have dfds, sigma s delta Brownian motion, and we have minus dfds sigma s delta Brownian motion. So this term here cancels this term here. There's another cancellation, which is we have dfds mu s delta t, and we have dfds mu s delta t, which also cancel each other because there's a minus sign here. So we do all these cancellations and we're left with this. And just in the case where we constructed this portfolio when we were working with binomial trees, what we get is that the change in the value of the portfolio is known in advance. There is no Brownian motion here. There is no source of noise. When you look at this, this is a number. If you observe the price now of the underlying asset, if you observe what is S at time t, and you ask yourself, what's going to be the change in the value of this portfolio? Well, this is a number now, and this is a number, and this is another number, and this is another number. So by how much is your portfolio going to change in value? By this number times delta t. This expression is non-stochastic. There is no random variable there. This expression can be computed in advance of this time period between t and t plus delta t. Right? And what do we know about an investment whose price at some point in the future is known in advance? So if I tell you that if you invest in this stock, you're going to get £1 exactly in 1 year, then what do you know about investing in this stock? Investing in this stock is the same thing as putting your money in a savings account. In other words, the price of this stock now must be the present value of this known value in the future. So investing in this stock is the same thing as going to the bank and depositing your money at an interest rate of R. So this is one way we can think about the change in the value of the portfolio. But now we can say, since the change in the value is known in advance, investing in this portfolio is the same thing as putting your money in the savings account and getting a risk-free interest rate of R. And what happens when you deposit £pi into a savings account giving you an interest rate of R, by how much does the value of your investment change? So after delta t years, if you start with £pi and you're getting an interest rate of R, you're going to get a balance of e to the R times delta t times the initial value of the portfolio. And if you want to know by how much your investment value changed, well, you have to subtract pi from this. This is what you get after delta t years. This is what you invested. This is the change in the value of this investment, of this portfolio. And now we're going to do one more step. We are going to say if delta t is very small, then e to the r delta t can be approximated by 1 plus r delta t. I'm just looking at the Taylor series of the exponential function. And if I use this approximation for e to the r delta t, when I look at the change in the value of the portfolio, I'm getting this minus pi, and this plus pi minus pi cancel, and I'm just left with this. Okay? So now let's write this down. What is this telling me now? So on the one hand, I just got the change in the value of the portfolio to be what is written over there, so it's R. Now I have to write pi. Now let me remind you what pi was. Pi was delta F delta S. Delta F delta S, S minus F. So I'm just writing down the definition of the portfolio again. So here's my portfolio. And now, on the one hand, we're getting that as a change. On the other hand, I'm also getting this calculation we had in this slide, which is minus 1/2 the second derivative of f with respect to s times sigma squared s squared minus df dt. So on the one hand, I'm getting this times delta t. On the other hand, I'm getting this times delta t. I can go to the delta t's and cancel them. And I'm getting the equation that says that this is equal to that. And now I'm going to rearrange these terms, and I'm going to end up with this differential equation. So if we now rearrange things around, if you bring all this to the other side, and you take this r times minus f to the other side, we're going to get this equation. And what sort of thing is this equation? How do we call an equation like that? It's a partial differential equation, a PDE. Why is that? Because you have this function f, and you have a relation between the values of your function f and its various derivatives. So f is a function of two variables, of s and t. So you have a relation between f and the derivative of f with respect to t, and the derivative of f with respect to s, and the second derivative of f with respect to s. So we're getting a relation between the values of a function and its partial derivatives, and this is what we're calling a partial differential equation. Who has seen partial differential equations before? Raise your hand. Okay, so if you haven't seen them before, if you really haven't seen them before, and you want help with them, then come to my office hour and I'll remind you what these things are. But this is great, because now what is this saying? What is theorem 6.2, which we just proved, is saying? Saying, do you want to find the value of a derivative, the price of a derivative? Just solve this differential equation. So now we can forget about stochastic processes and Ito's lemma. You want to know what f is? Well, solve it, right? But of course, life is not as simple as that, because partial differential equations are first difficult to solve, and there are zillions of solutions. And you have to choose the right solution for you. So let's talk about the right solutions for us. And let me remind you what happens with ordinary differential equations. So suppose that I come to you and I ask you a very simple question. I say, I have a function y of t, and it satisfies dy dt is equal to 1. And I ask you, what is y? Then you're going to say, let's integrate both sides. Y of t is t plus a constant. So, do you all agree that these are the solutions for that? Okay. But now, which is the solution I'm looking for? This condition, this differential equation is not enough. I have to specify more. I have to tell you a bit more information. For example, I can tell you what's the value of y at 0. So if I tell you, y of 0 is 5, then they're going to come here and say, so if that's the case, then you have to take c is equal to 5. Yeah? Do you remember doing things like this before? So what am I going to do now? So now we have a differential equation, which is a partial differential equation. The solutions of this partial differential equation are going to be functions of two variables. So there is going to be the t variable and the s variable. And suppose that I'm talking about some derivative paying you a payoff at time t, at expiration time t, then if I'm talking about finding the solution of this problem, which is going to give you the price of this derivative, I'm talking about finding f of s and t for any point in this region, right? So, okay, I know that f satisfies the partial differential equation. We expect that not to be enough to determine what f is. What else do I have to give you? Well, I have to give you some extra information. So in this case, I gave you the value of your solution at one point. Now I have to give you the value of your function at the boundary. So, for example, I can say, I'll tell you what's the value of the function here, and I'll tell you what's the value of this function on this infinite boundary. So I'm going to tell you what is f of NES and t, this t here, and I will tell you, say, what is f of 0 and t for t's between 0 and capital T. Okay? So if I give you that information, maybe I have the chance of telling you what is the price of your derivative. It's going to be the solution of this differential equation with these boundary conditions. In other words, well, some people call this the solution of a boundary problem. So to find prices of derivatives, we have to impose extra conditions, these boundary conditions. So for the case of a European call option, I'm going to give you the value of the function here. So what is the value of the function here when f now is the price of a European call option? So in the case of a European call option, f of s at time t is the payoff of your option. It's the maximum between s at time t minus x and 0. I don't know why I'm writing red. Let me do the other one in some other color. And then what other boundary can I specify for you? Do we know what happens here with the European call options? So suppose that we have European call options on shares of IBM, and we find ourselves here. What happened to IBM? What's this point? It's on the t-axis. So what is s? The s-coordinate of this point? 0. So what is this telling me about share prices of IBM? They're worth 0. How do you call a company whose share price is 0? You can buy any number of shares for 0. That company is what? It's dead. It's bankrupt. What happens to something once it's dead? It stays dead. That's what dead means, right? So if your company was dead here, it's going to be dead here and here and here and here and here, and it's going to be dead at expiration. How much is a call option worth when the underlying asset is worth nothing? There are various ways of spelling this with N's and Z's. So, in the case of a European call option, the boundary condition is that the value of your function, your price, here is 0. Okay, so here are boundary conditions for call options. Now let's see if I can use a different color, which is more legible. How about put options? Now f of s and expiration time is going to be the maximum between x minus st and 0. The payoff you're getting from this put option at expiration. And how about the boundary here? So again, if the company at this point goes bankrupt, it's going to remain bankrupt, and then you know that when you get to expiration, you're going to get a payoff of x. So now f of 0t is what the present value of what you're going to get for sure at expiration, which is x. So it's e to the minus interest rate times to expiration, which is big T minus little t, times x, when x is the strike price, I should have said. Right? Are we happy with this? Do we have any questions about any of this? Okay, so we have those boundary conditions, and then once the underlying asset is worth 0, it's worth 0 forever, and then we can impose boundary conditions on European calls and puts. And now we say, fine, so you want to know what's the price of a European call option or European put option? Here is a partial differential equation with these boundary conditions. Just find a solution for that. Do something and find a solution for that. Okay, so that's what I'm going to do next. No, sorry, that's not what I'm going to do next. I'm going to give you an example. But before I give you an example, let me tell you something that is terribly important. Otherwise, we can't do the next example. So the terribly important thing is this. So if you look at this kind of partial differential equations, so if f satisfies the differential equation I gave you, which is what we're calling the Black-Scholes partial differential equation, named after two people called Black and Scholes, who discovered this. So if f is a solution of this partial differential equation, and if you specify the values of this solution along this boundary and along this boundary, then there is a unique solution of the Black-Scholes partial differential equation satisfying these boundary conditions here and there. So unless, I should be a bit careful, if these boundary conditions are not too crazy, and we're not going to see any crazy boundary conditions, then there is a solution. And not only there is a solution to this problem, to this boundary problem, but there is a unique solution. So let me show you how we can use that. This is terribly useful. So let me give you an example of finding a price of a derivative. So let's start with this function. We have a function of s and t, and I'm just giving this, it's coming out of the blue, and it's given by that expression over there. So I want to use this function to construct the price of a derivative, and I'll show you how that happens. But the first thing is, let's remember what it means to be a solution of the Black-Scholes partial differential equation. So what do I have to do to convince you that this function is a solution of the Black-Scholes partial differential equation? Well, I have to compute the various derivatives. Here they are. And then I'm going to compute the left-hand side of the Black-Scholes partial differential equation. Here's the left-hand side of the Black-Scholes partial differential equation. And then I'm going to substitute my expression for dfdt. There it is. I'm going to substitute my expression for dfds and for the second derivative of f with respect to s. And I'm going to get this enormous mess. And then I'm going to simplify this enormous mess. And it's going to simplify to r times f. And r times f is great because it's the right-hand side of the Black-Scholes partial differential equation. Okay? If this is looking like something unnecessarily complicated, well, yes, it's very complicated and very non-interesting. It's just a question of finding derivatives and plugging them in. What we want to take from this technical slide is the fact that I just gave you a function which happens to be, by magic, a solution of the Black-Scholes partial differential equation. So now let's take this and let's see if we can do something useful with that. So now let's dream of a derivative. This derivative has a payoff which is a function of the underlying asset price, which we're calling S, and it gives you a single payoff at time capital T greater than 0. And how big is your payoff? Well, it's some power of the underlying asset price you observe at expiration, some power of ST, and which power it is the 1 minus 2 times interest rate. So we're assuming that all interest rates are the same and they're equal to R, divided by sigma squared. So sigma was the volatility of the underlying asset price. It's what we observe. The same sigma you observe in the Black-Scholes partial differential equation. So we have this derivative that is going to pay us this much at time t. And we're going to assume that this makes sense, so I want this number over here to be positive, and I'm going to find for you the price of this derivative at any time between 0 and expiration. And here's the trick. So instead of looking at one derivative, let's have a look at e to the RT derivatives. R is the interest rate, T is the expiration time of this derivative. And let's give a name to the price of this portfolio consisting of this number of derivatives. Okay, so let's ask ourselves, what do we know about the value of this derivative? We know that V at expiration, so if you get to expiration time t and you find what S of t is and you plug in into the value of your derivative, so what do you get? Well, you're going to get each unit of derivative. Each derivative is going to give you this payoff, and you have this many of them, so the value of the derivative at expiration is given by this product. And if you go back to our function, the function we started with, here it is. If you look at f of st at time capital T, what you're getting is exactly the same thing. You're getting this. What else do we know? What is v of 0? Well, v is going to give you a payoff which is some power of s, and if s at any time before expiration is 0, it will remain 0, so you will get to expiration time and you will get 0 to some power which is 0. So v of 0 and any t is 0, and your function f, which was e to the something times some power of s, if you plug in s is equal to 0, that's going to give you 0 as well. So we have that v of 0t is the same thing as f of 0t. So we have two functions, f and v, whose values here are the same. That's what we've just done. Whose values here are the same, which corresponds to little t being big T. And they both satisfy the Black-Scholes partial differential equation. Now, I did a calculation, and I showed you that f satisfies the Black-Scholes partial differential equation. How can I claim that v satisfies the Black-Scholes partial differential equation? Because what is the Black-Scholes partial differential equation? It's a partial differential equation which is satisfied by the price of any derivative. Now, v is not quite the price of a derivative, it's the price of some number of derivatives, but the Black-Scholes partial differential equation, as you notice in your homework, is linear. So if the price of one derivative satisfies the Black-Scholes partial differential equation, then some number times that price is still going to satisfy the Black-Scholes partial differential equation. What I'm saying now is terribly important. Do you understand what I'm saying? Do you understand what do I mean when I say that the Black-Scholes partial differential equation is a linear PD? Sums of solutions are solutions. Solutions times the number give you another solution. Okay? So V itself being the number of the price of a number of some derivatives, so we have, say, 17 derivatives. So the price of the derivative satisfies the Black-Scholes partial differential equation. 17 of those is still the solution to the Black-Scholes partial differential equation. So both V and F are solutions of the Black-Scholes PDE. And then what did I say before? I said if you look at solutions of the Black-Scholes partial differential equation which satisfy some given boundary conditions here and there's going to be a solution, and there's going to be a unique solution. So what do I deduce from the fact that the solution must be unique? I'm showing you two solutions, so what do we know about these two solutions? If I'm saying there is unique such choke, there is no choke like this, but this one, and then I say, look, here's another one which satisfies exactly the same conditions as this unique choke. So what do I know about these two chokes? You're seeing double. It's the same choke, right? if there is a unique something and I'm showing you two of those, that the two things are the same. So in our case, V must be equal to F, which is great because we're trying to find what V is, or at least a multiple of V, and we know what it is because F is this strange function I gave you at the beginning. So what do we know? We know that the price of this portfolio consisting of e to the RT derivatives is F. There it is. V is that. Now, what is the price of one derivative now? This is the price of e to the R capital T derivatives. So to find the price of one derivative, I divide by that, and I get this, which I can rewrite in this form. This example is very important. So let me pause and ask you if it's making sense. Do you understand this example? Can you nod your head, shake your head, shrug your shoulders, ask a question? Would you like me to tell you the story again? People are saying, no, just leave us alone. Fine, okay. Right, so we're ready. I'm going to show you the prices of European call options and put options, and that's going to be almost the end of this story. So here it is. So we're looking at some underlying asset price whose price follows the process S, which we've written down several times. Let's define two numbers. I want to know what is the price at time little t before expiration of this derivative. So I go to time t and I observe the price at time t and so on. And I observe the strike price of these options you're talking about and the interest rates, which we're assuming are always the same and equal to R, and the volatility of the underlying asset, which is what we're calling sigma. And we can compute this number, and we can compute this other number, which is exactly like the previous one, only there's a minus sign here. That's the only difference. And now, do you want to know what the price at time t of a European call option expiring at time t with strike price X and so on is? Well, there it is. So you take the observed underlying asset price at time t, you multiply this by phi of d1. So what is phi? That's a standard normal distribution function. So phi is this thing that you look up in tables and which give you, so here's the distribution function of, let's take the density function of this standard normal random variable, which is this bell-shaped thing. And then if you, let's call this y, and let's call this x. And if you look at phi of x, what is phi of x? It's the area of this. It's a distribution function of a standard normal random variable. So you computed this number d1, you plug it into your phi function, and then you also have to take phi of d2, and you have to multiply this by the strike price times e to the minus r times time to expiration. That's what big T minus little t is. And that's it. That's the price of your call option. And if you want to know what's the price of your put option with the same strike price and same underlying asset and all that, then, well, it's this other expression, which involves the D1 and the D2, which we computed here, and the strike price, and time to expiration, and the underlying asset price at time t. Okay? So I promised to show you this, and I'm showing you this. But now you should say, why on earth, where is this coming from? And this is coming more or less out of the blue. So what do I have to do to convince you that this is true, that this theorem 6.3 is true? So let's concentrate on the prices for call options. I have to take this function of S and time. So if you just look at this, there are S's in them and there are times in them. So you can think of this as a function of S and time. And you can find the derivative of that function with respect to t, and the derivative of that function with respect to s, and the second derivative of that function with respect to s. And then you can take all these partial derivatives, you can plug them into the left-hand side of the Black-Scholes partial differential equation, and you're going to do lots of calculations, and you're going to have to show that that's the same thing as the right-hand side of the Black-Scholes partial differential equation. So if you do all that, you're going to be able to verify that C is a solution of the Black-Scholes partial differential equation, which is great. What else do you have to do? You have to show that it satisfies the right boundary conditions, these red boundary conditions, which we wrote here. This one over here and this one over there. So again, you roll up your sleeves, you ask yourself, what happens when you substitute s is equal to 0 into this function c? You should be getting 0. What happens when you try to substitute little t is equal to big T? Are you going to get that c of s and capital T is equal to that? And if you do, then you have a solution of the Black-Scholes partial differential equation which satisfies the same boundary conditions as the prices of call options. So this function that I'm just producing out of the blue must be the same as the price of these call options. Why is that? Because the prices of call options and this function I'm giving you, you verify the solutions of the Black-Scholes partial differential equation. They satisfy the same boundary conditions. And I told you, these boundary problems, these PDEs with specified boundaries, have unique solutions. So these two things I'm showing you must be the same. So this C must be the price of the European call options. Okay? Do you understand what I would need to do to show you that C is indeed the price of European call options? Okay, am I going to do that? No, because it's going to be really boring. So this is a bit disappointing, but you need to verify that when you take your function C that they just gave you explicitly, you compute the left-hand side and you get the right-hand side. You can't quite plug in little t is equal to big T because things are going to blow up, but you can look at the limit as little t goes to big T of your function C, and you're going to get it, you're going to see you're getting the right boundary condition here, and you can also check what happens when s goes to 0, and you're going to get the right boundary condition here. And then by the uniqueness of these solutions for these boundary problems, C must be the price of the European call options. And you can do the same thing with the function P, and you can convince yourself that it must be giving you the price of European put options. So this is a bit of an anticlimax because I'm giving you the promised solution, but then when I'm supposed to show you that this is really the solution, I say this is too tedious. Trust me. But it is really tedious. I've done this once in my life, and I don't wish to do this any more times. But at least we know what we should be doing in order to convince ourselves that we have a solution for something. So again, this is terribly important. Let's pause for 10 seconds and see if you can come up with any questions about this argument here. Okay. I'm trying to figure out what to do during the next 5 minutes. So maybe I'm going to have to finish this next time. But let's go back to the very beginning of this course. So we started by asking ourselves, what is the correct price of something? And then we said, well, let's instead ask ourselves, what is an incorrect price of something? And then we said, an incorrect price is a price that allows arbitrage opportunities, free lunches. Okay? Now I'm standing in front of you and I'm saying the correct price of these call options and put options is that. And to do that, I didn't cook any free lunches. I just looked at some partial differential equations, and I did this and I did that, and I checked boundary conditions. So in what sense is this price I just produced for you correct in the sense that we began this course with? In what sense this is a no arbitrage price? At some point we assume that there are no free lunches. What was the point where we assumed that there are no free lunches? Do you remember when we constructed this portfolio, that no matter what happened after a short period of time, it had the same value? So we have df, ds shares and -1 derivatives. And then we check what happened after a very short period of time. It had the same values in all states of the world. At that point I said, since the value of this portfolio is known in advance, then the value now must be the present value of the portfolio after one step in time. When we made this argument, that's where we're using a no arbitrage argument. Whenever I say, if this is going to be worth £1 in a year, then now it must be worth the present value of that, which is e to the minus interest rate times 1 year times the value of this. Okay? How do we prove that? We said, if that's not the case, if the price is bigger than that, or lower than that, we can produce a free lunch. That's how I convince you that this is the case. So at this point, when we took this very short step in time and our very carefully constructed portfolio at the same value in all states of the world, and then we said, so the value now must be the present value of this certain future value. At that point, I use a no arbitrage argument. So our price we just produced using all this fancy stuff is still a no arbitrage price. So we use fancy things, but our definition of correct prices is the same one. Okay. Let me just skip these things. I have 2 minutes left. Okay, let's continue this next time.